All right, so we're honored to have the opportunity to have a conversation with Kevin Buzzard, a professor of pure mathematics at Imperial College London, who specializes in algebraic number theory and is an enthusiastic evangelist for Lean, a computer software which verifies proofs. So let's start all the way back to the start of your journey. So what made you interested in mathematics?
It's the only thing I could do. It was the thing I was best at, and most of the things I was quite average at, so I just went with it. And I liked it.
And so people look up pure mathematics and say that there aren't many practical applications and say, what's the point of studying it then? What would you respond to that?
Yeah, I totally agree. There's no point in studying it at all.
So what drives you?
I just think it's a really fun game. It's like, so what's the point of playing chess?
Yeah.
But you see, that's not everyone's answer. Right? That's my personal answer. I'm a formalist, and I think that mathematics is no more. It's just a game like chess. Whereas there's plenty of other people in my department, even though say mathematics is important because we can solve differential equations and we can model reality. And, so mathematics is really important for those reasons. But that's not why I do it. I'm a pure mathematician. I just do it for the fun.
Fair enough. It is very interesting.
Could you explain what branches of number theory you mainly do your research into?
So my advisor, Richard Taylor, and his advisor, Andrew Wells, proved Philomath's theorem. And they proved it using these things called elliptic curves and modular forms. That's the idea. Modular forms and generalizations of them when I'm doing number theory research. But we have a definition of a modular form in Lean and an elliptic curve. So it would be nice to teach Lean the proof of Philomath's theorem. Unfortunately, it's going to be a really long journey.
How long do you think it will be before you could get Lean to verify the proof of Philomath's last one?
It's going to be a long time because it's going to take a lot of person hours. It's definitely possible, but it's going to take a lot of person hours because we just basically need to build. In the 1960s, there was a whole lot of algebraic geometry sort of invented or discovered. Just like Alexander Grothendieck. So we've got to sort of type in the 10 years of work that he did, him and his students between 1960 and 1970. And we've got to type in a whole bunch of analysis that Robert Langdon's did around the same time. And we've got to type in a whole bunch of 19th century mathematics that it all builds on. And the problem is that we haven't got the staff. Right? Because most mathematicians can't speak the language yet. Right? That's what I'm trying to change. Right now it's going to go very slowly. I mean, I know how to do it. It's going to take 100 years, sort of thing. Unless we get other people involved, then it'll be quicker.
Are there any interesting mathematics topics which you would recommend to students, such as ourselves, to research further?
Oh, just do what you like. Just do what you're interested in. When I was your age, I was doing Olympiad problems because that was, because I needed challenging. These things were challenging. But, I'm not. Olympiad problems are sort of a weird part of maths, really. They if you're quick, then you might be good at them. But being quick isn't actually necessarily a skill that's important in mathematics. It is something. But maths is like a marathon, really, not a sprint. And these Olympiad problems encourage sort of racing because you have to do these things. The kind of problems I solve now, you haven't got years to solve them, whereas in Olympiads you've got an hour and a half or something. So in some sense, I don't approve of those kinds of problems. On the other hand, you could learn undergraduate mathematics. You could go and learn what a group is and a ring is and a field is and what a vector space is. But then again, should you be doing that now? I mean, why don't you do that when you're at university? Maybe you should just be learning random stuff. Just go and learn random things. Just go and watch some YouTube videos.
Talking about mathematical Olympiads, you you got a perfect score in the IMO, and then you went on to get be awarded the title as a senior wrangler.
Yeah.
So what's the secret behind your success?
I was at some point incredibly fast. Right? As I say, it's not a skill which is necessary. I mean, it's a very useful skill if you want to be top in exams, but it's not a useful skill if you want to be a good research mathematician. It's sort of handy. So I vividly remember standing on that stage in Cuba in 1987, with my gold medal and my perfect score at the IMO, just looking around at the room, thinking these people are, future mathematicians. These people are going to be my colleagues in future years, and we're all maths professors proving new things. And 5 years later, I realised I was completely and absolutely wrong, because there were all, many of the people on the Maths Olympiad team that I was on, they all went off to university with me, and they just got degrees and they just lost interest. And they got degrees, graduated, and went and got jobs. And some of the people that came up and were turned out to be brilliant, brilliant mathematicians, were people that their school didn't even do the Olympiad or whatever. It's just being able to be very fast doesn't make you a good mathematician. It just makes you good at one sort of thing. And now, the people I work with, some of them went to the IMO, but some of them, just didn't go at all. They just say, "Oh, I'm no good at it." But they turn out to be great researchers because they're capable of thinking very hard and very deeply about a problem for a month. As opposed to being able to knock off a quick combinatorics problem within 20 minutes, which is the kind of thing I could do. But that's not the same as mathematics.
So you're a researcher in mathematics, and what does research in mathematics involve? What do you do day to day as a professor?
I mean, in practice, unfortunately, I spend a lot of time filling in forms and going to committee meetings, refereeing grant proposals, and hiring new people. There's a whole bunch of admin that just piles up as you get older. But when I'm not doing that, I'm doing research. I mean, right now, what I tend to be doing, 5 years ago, the answer would be very different. But right now, what I tend to be doing is we're trying to translate some profound work by Peter Scholze, some field specialist, from his paper he wrote into Lean. And so I read that paper and try and understand it from first principles. And if I understand it, I type it into Lean. And if I don't understand it, I start asking questions to people like Peter Scholze. So that's what my day-to-day work is now. I'm a translator. And the reason that's research is because we're translating mathematics that no one's ever translated before. It's very high-level mathematics. We're the first people to attempt to study modern research mathematics within the context of any theorem proof. But 5 years ago, I was doing something different. 5 years ago, I was thinking about generalizations of Fermat's last theorem. Just drawing pictures on pieces of paper. Trying to prove abstract theorems which are slightly more general than theorems in the literature. Or trying to figure out new ways of fitting things together.
Talking about research with Lee, why is your research primarily with maths undergrads as opposed to postgrads?
Yeah, that was quite weird because when I was a number theorist, it wasn't like that at all. I would work with PhD students, and Fermat's last theorem is a very hard piece of modern mathematics. I mean, he's not that modern anymore. He's 25 years old. You can't begin to understand that work if you're an undergraduate because you don't even know the definitions of the things involved to prove it. So I used to only work with people with PhDs, basically, or people who were training to get PhDs. But when I switched to doing Lean, all of a sudden, the maths library was primitive when I switched, right? This maths library, we didn't have sine and cosine, so we couldn't do half the stuff in the first year. And we had to make it, basically. So it was a sort of an interesting project. So we started making bits and bobs. And then we started making some harder things. I tried to make some MSc level stuff, something called a scheme, this thing in algebraic geometry. So me and a couple of undergraduates made schemes. And then we started asking, we were just doing it for fun. I have a club on Thursday evenings, so we were just goofing around and trying to make schemes. And then we made schemes. Then I started asking how it was done in the other systems. because it turned out it had never been done in the other systems. And people were telling me, oh, we should publish. And I'm just thinking this was just something we were doing for fun. It was just a project. We didn't realise that we were doing original research. We just thought we were having fun making maths. And it was at that moment that it dawned on me that there was a huge amount of stuff that we could just do here. Because I'm a maths researcher, and I have a shed load of mathematics. It's even something as basic as a scheme, in the sense that it was invented 50, 60 years ago now, 62 years ago. But like, no one had got around to doing it in a theorem prover, because theorem provers have existed for decades, but they're used by computer scientists. We just are interested in a different kind of mathematics. You know, they're very interested in induction and in logic. But they're not interested in the kind of mathematics that proves certain that's theorem, because that's research level. You know, that's something that they're teaching computer science. Why would they? Right, it's mathematics, it's not computer science. So it just turned into this whole new research. You know, I just realised there was a huge opportunity. It's like, why don't I make a bunch of the maths I know? Why don't I start translating my papers into this language? Because it would just be an interesting stress test of it, to see if it worked. Right? We know we can do MSc level mathematics. You know, can we do perfectoid spaces? These are really fancy modern objects invented a decade ago. So we tried to do perfectoid spaces and it worked fine. So I forgot what the question was.
The question was, I was asking why you were primarily doing research in Lean with undergrads.
Oh yeah. So it just turned out that it was a really good way that undergraduates could write papers. Yeah, they were just the kind of maths that needed to be done in the system at the time was the kind of maths that undergraduates knew. It's getting to the point now where the kind of maths that needs to be done is the kind of maths that PhD students know. So I might be working less with undergraduates in the future because we want to grow this stuff. Yeah, so you might. It's a shame, really, because I really enjoyed working with undergraduates, but it might be back to PhD students now.
Why do you think formalising mathematics in a software such as Lean is so important for the future?
Oh, it's just been experiment. It's blue sky recent. I have no idea where it's going, right? But you know, it's like if you ask the person that made the CD, right? I'm old enough to remember I was buying vinyl in the 80s, and then in the late 80s, CDs came along, and I was like, yeah, buy CDs. You know, they're more expensive than vinyl, and you've got the vinyl already. But you know, so you kind of felt this is some sort of weird trick, right? I've got the vinyl. I'm not going to buy the CD as well. But then new things come out, and you kind of think, well, you know, I've got to buy this new thing, so I will buy a CD. You ask the people that invented CDs, what's the point of digitising music? Because that's what's doing, right? On vinyl it's stored as analog, and on CD it's stored as digital. So you digitise music. So what's the point of digitising music? They're never going to say all the things that we use digitized music for now. Right? They're not going to say, oh, because then in the future we'll be able to have Spotify. Right? In 1989, there wasn't even an internet. I mean, there was an internet, but you couldn't do it. There wasn't a web, right? It's before the World Wide Web. And the smartphone, these things just weren't there. So, you know, the point of, if you could do something on the internet, then like, who has access to that? Like, you know, it's people in universities have got access. Yeah, not normal people. It's like it took 30, 20 more years before normal people got access to the internet. And then you kind of say, oh, this is great, you have Spotify, you can store all this music online, you can store it digitally. So it's just the same as we can store mathematics digitally. Right? You know, you could write a book and then save it as a PDF, but computers can't read human language yet, whereas they can read Lean. Right? Because it's digitised mathematics. So we're digitising it and we don't know. We don't know what the point is. But we'll find out. You know, maybe they'll make an AI that's better than all of us at mathematics. But they might not. But maybe they'll make a great, I don't know, maybe they'll make a great new way of teaching geometry. I don't know. Or maybe they'll make a tactic which helps PhD students doing algebraic geometry. Because algebraic geometry is a vast area. And we prove that they can do it. You know, we define schemes, we're defining other things. We've proven theorems to have schemes. These poor old graduate students, they've got to learn algebraic geometry, they've got 7,000 pages of stuff to read about schemes. Right? Where are they going to start? Well, actually, they've got this system in front of them where they can type in questions and say, is this right? And you know, it can look through a database and try and construct a proof from what it knows. And say, yeah, this follows from theorem 4 of this paper. theorem 6 in this book, or oh no, this is wrong because I've got a counterexample in my database. I think that might be a thing. But yeah, we'll see. It just feels to me like digitising something is just making it more flexible. We can use it in new ways.
So would you say that's similar to how you describe the importance of proving problems like Philomath's theorem? We might not have a use for it now, but it might lead us to find something else in the future.
I think for Fermat, it's very unlikely to help us. I mean, Fermat's theorem is really it's the end of it. It's a challenge problem, really. But what formalising Fermat's theorem will teach us how to do is how to teach difficult mathematics to a computer. It will just give us more understanding of the difficult problem and how to teach hard modern mathematics to a computer. Because that's just something that people haven't been working on. To my surprise, I just thought it was a very natural thing to do. But they made loads of these systems that could check mathematical theorems, and they just kept proving things like square root of 2 is irrational. Just make another system, prove there's infinitely many prime numbers, prove the square root of 2 is irrational, and say, well, look, it works. But let's just experiment and work out how to store mathematics on a computer. Because that's what blue sky research. That's no different to what I was doing 5 years ago. And I was trying to work out various theories about p-added modular forms. They're not going to be very used to p-added physicists. I think such really thing. But it's a certain part of the university is devoted to the blue sky research, and that's what this is. Really. Just all a big experiment. We'll see if something useful comes from it.
I assume while working at uni, you've worked with a lot of computer scientists.
Oh yeah.
What would you say is that computer scientists think about Lean and its applications?
Well, they've seen it all before. They've had software like this for 50 years. So they don't. It's just no different to any other theory. The big difference is that mathematicians have figured out how to use them, whereas they never somehow figured out how to use the other software. The computer scientists, I think they're all a bit bewildered by the whole thing. Because they don't, we make structures like schemes. So I made the natural numbers as an MJ. I made schemes, and they just see schemes as like the natural numbers. They're just a definition. I just made a big definition. So to make a scheme, you have to do it in the following way. And they're like, big deal, because they're not interested in schemes. I think that they're just observing the mathematicians are using these tools, and it turns out we're using them in new ways, which are getting other mathematicians excited. But I think in some sense they just trust that we know what we're doing. And maybe we don't know what we're doing. I think they're just pleased that it's caught on in a different community. That was the problem 5 years ago, is that no mathematicians were using this software. Not just Lean, any of the software. There's Conk, and there's Isabel Hall, and there's Holnight, and there's Marizon, and there's Metamath. No mathematicians use any of them. Not good, or very few. Now we're hoping it catches on.
So why do you think it's taking so long for mathematicians to use automated theorem proving?
I just don't think that mathematicians can see the point. And it took a while to convince them, right? I made schemes, and I'm going, this is awesome. Like, this is something, 50 years ago, no one's ever made it before. We made schemes. But the computer scientists just going to me, it's just a structure. You just made another structure. You just made another object. Great big deal. And what's the point of it? They said. And I'm telling the mathematicians, we made schemes, and people in my department are just saying, well, I knew what a scheme was when I was an MSc student. Nobody thought it was a big deal at all. And so I thought, all right, let's make something really complicated. Let's make vectoring spaces, because they're difficult modern mathematics, and I know the definition. So we made that, and the computer scientists were like, what's the point of vectoring spaces? But this time, the mathematicians were like, whoa, you make vectoring spaces, those are really complicated. And we're like, told you, isn't it interesting? Now let's make some other things. And so that was how the mathematicians started coming on board, just because it was as I said, I've got this paper where I define perfectly spaces, and it's you know, just out. It's like no other paper. It's a completely bizarre thing. I don't know who refereed it, but it was just to prove to the mathematicians. It was just to try and show mathematicians what could now be done, and probably it could have been done like 10, 15 years ago. Just nobody did it, so it was a publicity stunt, really. But things have really snowballed from that, because now people have said, "Oh, can you prove this hard theorem?" And I'm like, "Yeah, we can do that." Yeah, we've taken specific, difficult theorems, and we're trying to prove those theorems as well, just to try and get the maths community on the side. But yeah, we've got to wait for the killer application. And that was the trick. Just this gimmick. We just showed that we just took something that had been done in maths 3 years ago, and we just did it in real time. It took us 8 months.
Hey, so I guess to round things up, we have one final question. And that is, what advice would you give for students? Just any advice, whether it be
Don't listen
maths
to
or
me.
life advice or anything.
Yeah, don't listen to grown-ups. Do your own thing. That's my advice. Yeah, just ignore your parents. And me. That's my advice.
Okay, so thank you so much for letting us have a conversation with you. It was very insightful. We hope that you make great progresses and lean in the future. And hopefully we might be able to join on the journey as well.
Brilliant.
Yeah.
Thanks very much.
Yeah, no worries.